in here. All right, welcome. This is AE514. I'm Dr. Steck. My office is upstairs in 218. It's on the syllabus. I'll show you that in a minute. But it's easy to find. Just go up the stairs in the back corner, and my office is right there next to the freight elevator. I'm going to switch over to the syllabus. This should be online, so you can grab it at any time. Do the people on Zoom, does that look backward?
No.
Oh, somebody says no. Okay, good. But to you guys, does it look okay? That's weird. I've never totally figured this out. I can't switch it there because it's going to be backwards on Zoom. Oh, I know. Here, I know what I need to do. Here we go. Where did it go? Well, maybe we'll have to talk through it. It should show up there on the document camera here. All right, well, you've got this online. Let's talk through it. Again, I'm Dr. Steck. My office is in 218 upstairs. The way office hours work is that I'm almost always there during the office hours, and I currently have them set right before this class on Mondays, Wednesdays, and Fridays. If you need to see me outside those hours, you can come by. If I am there and I have time, I'm not busy doing something else, I'll be happy to talk to you. If you need to see me outside office hours and you want to make sure you can, just email me and we'll set up a time. I will do optional Zoom as well. If you want to talk to me over Zoom, just shoot me an email and I'll send you a link that we can use to Zoom for office hours. Let's see, what else we got? You guys all found the textbook? The Dynamics of Flight, it's listed on the syllabus. Make sure we do use this book quite a bit, so make sure you get a copy. Bunch of boilerplate stuff. You guys know there's no spring break this year, right? And the class format is hybrid. We've talked a little bit about that. You have an in-person day assigned to you on Blackboard. Make sure you check that. It's alternating Mondays and Wednesdays for the people in here. And then on Fridays, we have Alberg Hall 200, as well as this room for in-person quizzes. Most Fridays, there will be an in-person quiz. And then following that, I will be in here, and the lecture will be zoomed over to Wallace Hall 200 so the people there can watch from there. I think that will work okay. We'll give it a shot. If there are issues, please let me know as soon as you can, and we'll work on fixing them. Let's see, so just make sure that you know that there are in-person quizzes on Fridays. So plan to be here for that. And this class is not an online asynchronous class, it is synchronous. So I expect you to either be in person on your assigned day or zooming in and watching the lecture. I will try to post the recordings of these lectures. No guarantee as to how often that, or how fast that happens. It takes about an hour and a half to process each video. So I tend to go in there and I'll let it go and run, but sometimes I get a couple days behind of posting. But the intent there is you should attend in person, and if you want to go back and watch it again, you can on the posted video. All right, there is homework. I collect that online. Make sure that you scan and upload as a single PDF. Otherwise, it's really hard to grade. So I need one file, one video file. Let me switch back. The syllabus is not working that great anyway. So I need one PDF file uploaded. You guys, I'm sure, are used to doing this now. And so all the homework will be submitted by the due date on Blackboard online as one PDF file. And it will be graded there, so you'll look for your grade and comments online. Quizzes are in person on Fridays. We've talked about that. And the grade breakdown in the class. Quizzes are worth 300. The homework is worth 100, and then we have a final that's worth 100. And you guys need to call me out, especially on Zoom, if I write too small and you can't see it. Camera is a high-def camera. I just want to make sure I'm writing big enough that you can see it when you're watching it. Remind me not to do that again. Actually, Dr. Rollins was telling me that if you stand right in the middle, somehow it does that. It gets some kind of feedback, so I need to watch out for that. So questions about attendance in class, how the class is going to run, or the grading policy? Anything? Let's see what we got on the chat. I think it's the syllabus. Yeah, it was the camera that I need to work on the Elmo and see what's going on. I don't know what the potato quality is like. Okay. On the third page of the syllabus is an outline of what we're going to be doing each day. It varies a little bit, but there's reading assignments, so make sure you pay attention to where we are in the book when I'm lecturing, and that you're reading in the book as well. For your convenience, I've made the numbers of the dates that are Fridays red so that you know which day to show up. I mean, which part on the syllabus corresponds to the quiz days, but it's every Friday, so it's not going to be hard to keep track of. And then the rest of the stuff in the syllabus is just the boilerplate, the normal university stuff, telling you about all the services of the university. Okay, we're going to start with chapter 1 in the book, but before we do that, on this Friday, there will be quiz number 1. And you need to review some stuff from AE514. And it's not the whole class. I don't expect you to go back and do a final on that class. But I need you to look at the airfoil, lift, drag, and pitching moment plots. And in the textbook, this is sections 5.1 through 5.4. And then the finite wing stuff. You remember you did the 2D airfoil plots, and then you learned how to calculate for a finite wing. So lift and drag for that. And this is sections 513 through 515 for that. And then you remember, I'm sure you remember fondly, Appendix D. That's the airfoil data. So make sure you go back and remember how to pick off CL, CM, and CD from the airfoil data plots in Appendix D. It's all pretty simple stuff. You just look at the graph, you're given an angle of attack, you pick off the lift or the drag or the pitching moment. But if you don't go back and review it, it's been, what, 3 months since you've done this? Maybe more. Practice. Take a half an hour, and go back and review this stuff, because we'll be using some of this stuff in this class. And then the other stuff is from AE514. And not the whole class, but just go back and remember what the Euler angles are. Do you remember that from the class, right? You talked about orientation of a rigid body in terms of the Euler angles, psi, theta, and phi. So go back and review the definitions and the transformations. Remember the transforms, right? You had these matrices with sines and cosines in them. I don't expect you to memorize those, but just go back and familiarize yourself with what a transformation of an orientation is in 514. Oh, what is 514? Were you guys puzzled, or are you wondering what the heck? This is 415, Spacecraft Dynamics. All right, so any questions on what's up with that?
Dr. Steck?
A lot of this class has to do with vehicle motion, because it's flight dynamics. So we're talking mainly about airplanes. And remember from your basic dynamics class, when you have a rigid body, we have the motion of the center of gravity. So the center of gravity in an airplane is usually near the wing. So we have X, Y, and Z motion, linear motion, and that tracks the center of gravity, and we can track the center of gravity and follow the flight path. And we also have angular motions. We have roll, pitch, and then yaw of the airplane. And those are true not just for airplanes, they're true of a spacecraft or any other rigid body that has pieces and parts, and it can rotate and move. And they're governed by Newton's laws of motion. So really what we're doing in this class is spending time applying dynamics to an airplane. And then what makes it more complicated than just a point mass or any other rigid body is that we have aerodynamic forces. And so the forces in Newton's law are what make the equations more complicated. So for the vehicle motion, we have the linear motion, like X, Y, and Z, and we'll talk about linear velocities. And we'll have to define those a little further, because we talk about the velocities of an airplane either in the Earth-fixed axis, that is, it's flying north, south, or east. We also talk about it in an axis system attached to the airplane, where we have forward velocity, side velocity, and upward or downward velocity. But we'll talk about these, and then we have the angular motion. which is a roll, pitch, and yaw. And that's what I was showing you with the foam airplane. It's all Newton's law. So it's classical mechanics, it's not quantum mechanics. And you've seen these before, some of the forces, mass times acceleration, so change in velocity with respect to time. So this is our x, y, z linear motion. And then some of the moments is equal to the moment of inertia times angular velocity. And so this is the angular motion. Like I said, that for the aircraft, it's the forces and moments that get complicated because we've got to calculate how the air hits the airplane and creates these different motions or different forces. And so in addition to stuff that's kind of normal, like gravity, we have aerodynamic forces. Lift, drag, pitching moment, side force. We also have thrust that's acting on it. And maybe for a balloon, we would have buoyancy. So anything and any piece of the aircraft can create a force, like the wing generates a force. The fuselage generates a force. The horizontal tail generates a force. The vertical tail generates a force. The landing gear generates a force. So you have to add all those up and put those into the equations. So you'll see as we go along that we will generate the forces and moments from things like the wing, the fuselage. We'll include all those effects, the vertical tail, the horizontal tail. And then we'll look at the control. There are parts of the airplane put there for the pilot to be able to control the airplane. So there's the elevator, ailerons, the rudder, the flaps, and whatever else is added to the airplane. So this is one part of the class. This is an introduction today, by the way. One part of the class is, well, how do we generate the forces and moments and calculate the dynamics of the airplane? And along the way, we'll have concepts of pitch trim, which is kind of a statics kind of thing. And then we'll have stability, which is a dynamic or a motion kind of thing. What? They're having trouble reading the board? Did you see a chat come up? What's going on with the voice volume? So on my screen, I'm seeing the text good enough to be able to see it. Can you guys read what's up there, assuming that it was not mirrored? Yeah. Let me double check the video settings. It should be set for the camera there. Yeah, it's high def, original ratio. You guys on Zoom, are you doing this on a computer or are you trying to do this on your phone? Because if it's on a phone, it's going to be too small. Computer. I'll try to write bigger. I don't know why it's not coming through. All right, so with regard to the trim of an airplane, it's flying along. If we're in what's called trim, we have lift upward, weight downward. So that's the statics, right? We have sum of the forces is 0. We have thrust forward, drag backward, sum of the forces is 0. And the airplane is not rotating, so the sum of the moments is 0. So that's typically what we call trim of the aircraft. It's in equilibrium. Let's write that up here. I'll write it big. Ah, okay. Let's see if I can get another marker going. This one might be a little better. So that's what's called equilibrium. And we'll spend a lot of time in that, making sure that the airplane can fly. But then we want to know, well, what happens if, say, a disturbance like a gust comes along when we're in our equilibrium, and it might cause the airplane to pitch up. So vertical gust coming below, airplane pitches up. What is the motion after that? Does it pitch back down to the equilibrium, or does it pitch more up more? Or does it go like this through the sky? And so that's this, it's the motion of the aircraft. And one of the easiest ways to think about that type of behavior, the stability, is to forget about the airplane for a minute. And talk about a marble in a bowl. So there's a bowl, the marble's at the bottom. That's an equilibrium. Makes sense, right? It stays there. The force of the bowl upward balances the weight, and we're all good. Now, if we have a disturbance up to that point, then we say, what's going to happen? And the first thing we look at is there a force or a moment generated to return it back to equilibrium? What do you think? Looks like there's a tendency, right? It's because the normal force of the bowl is this way, but gravity's down that way, so there's a component of the gravity that's going to want to move it back. So that's the stability. And the other is the motion. What does the ball do? Does it roll back down here and stop? We don't know, do we? You're picturing a nice smooth bowl, right? Which means it's going to roll down and then go back at the other side and go back and forth. What's going to keep it from going back and forth forever? No, there's going to be friction. Imagine that we put a shag carpet on this bowl. It might roll down and stop at the bottom, right? With not much overshoot. Same thing with an airplane. We want to design the airplane so that if there's a disturbance, it pitches smoothly back and doesn't fall apart. Pitches smoothly back down to equilibrium and doesn't overshoot and go like this. Because you're not going to be happy as a passenger if you're trying to drink your Coke and the airplane's going through the sky like this, right? So we'll do a lot of work analyzing the Newton's laws of motion to see, well, what happens in response to a gust and things like that. How are we doing on time? 10:55. We're doing well. All right, we did that. We did stability. The other concepts that we'll talk about in class are stick, fixed, motion, and stick free. You go, what does it matter? Well, if the stick is fixed, it means that the pilot is holding the control stick rigidly. And we can analyze the stability with the pilot holding the elevator in the position for trim. Stick free means the pilot completely lets go of the stick, and we need to talk about, well, there's a trim tab that allows us to trim the airplane in flight so that the pilot can let go of the stick. And in this case, if a gust comes along, not only does the airplane respond, but the elevator may flop around in response to the gust, and that changes the motion of the airplane in response to that gust. So we'll talk about both of these. So you'll see that. It's just, this is a heads up that we will see two different kinds of stability, stick free and stick fixed. We don't take care of this in this class, but the first chapter introduces this, is that the pilot can affect the stability. Different ways. Just by the motion of his body attached to the stick, if the airplane pitches up, his body may pull back on the stick just because that's the nature of him holding onto it. But his response, his brain responding to what he sees on the instruments, can also affect the stability. And there are things that are called PIOs, the pilot-induced oscillation, where the pilot will see the airplane pitching up, will respond, and it'll cause the airplane to pitch down, and then he'll respond, and he'll actually cause it to go up and down like that. So the pilot, when you start getting human factors, then you get the psychology people and the people that do human factors involved in understanding how does the pilot interact with the airplane and how does the airplane interact with the pilot when he's flying it. Part of what we'll look at are what are called handling qualities or flying qualities. And there's a bunch of different factors that go into this. The first one is control power. Can the controls be held at a position that caused the airplane to fly? So we'll be looking at that, especially with regard to the elevator and the pitch trim condition. Can we move the elevator to a position that will cause the airplane not to pitch up and down? It will fly straight, and everything, this total moment on the airplane is zero, the lift equals the weight. Will the airplane fly in that flight condition? So the elevator must be able to do pitch trim. The rudder needs to be sized so that in a two-engine aircraft, if one of the engines quits working, then you need to be, that's called one engine inoperative. So one engine out. So will the rudder do what we want it to do? Also, can it decrab the airplane when we're doing a crosswind landing? And then the ailerons, can they roll the airplane fast enough? So that's control power. And then the other thing that we have to look at is yeah, maybe the elevator can be put in a position that trims the airplane, but the pilot can't hold it there long enough to fly from here to Atlanta. And we'll talk about control forces, and then we'll talk about a trim tab, which is an aerodynamic or mechanical device that changes the control forces so that the pilot can handle the airplane. So we'll deal with both of those. And then on page 14 in your book, there's something called the Cooper-Harper scale. And this is a rating from 1 to 10 with a bunch of questions that they ask a pilot when they go fly the airplane. So let's say that you're an engineer and you've designed an airplane and you've built it and it looks like it can fly. You get enough lift to counteract weight, you have enough thrust to go forward, the elevator can control the airplane, so you build it and you send the pilot up. He comes back down and you go, what do you think? And he goes, well, I think it's kind of okay, but not the best. You go, what do you mean? Well, you give him the scale where he rates it. He goes through a bunch of questions that determine, is it flying well enough that the pilots will like to fly it? How easy is your airplane to fly? How basically, fundamentally, will it sell to people that want to fly your airplane? So take a look at that. We'll briefly mention that a couple times during the semester. But this has to do with flying qualities or handling qualities as well. Good pilots can fly an airplane that doesn't have good handling qualities, but the workload is really high. And definitely when a pilot's trying to land an airplane in a thunderstorm, you don't want his workload to be high because your airplane wasn't designed well. So your goal is to have good flying qualities, good handling qualities, so that the pilot can fly the airplane easily. All right, page 16 may be the most important page in the whole chapter. And that's the axis system. For the airplane. So first off, there's an Earth-fixed axis system. And the way this works is we assign an axis system to the Earth, and we point X north, and then Y is east, and then Z is down. So in this room, which way is north? Wow, everybody's got this. And so east is that way. So X, Y, Z is down. All right, so then over here we have the airplane. So here's our airplane. Here's the center of gravity. This is the body fixed axis. X out the nose, Y out the right wing, and then Z perpendicular to both of those. So if we want to know where the airplane goes on the Earth, we want this axis system. If we want to know whether the airplane's climbing, we want this axis system. But if we want to know what the pilot is perceiving, we want this axis system. If we want to know, well, where's the relative wind coming in to the airplane so that we can calculate lift, drag, and pitching moment, we want that axis system. And so this is where the Euler angles that we talked about, or I said you need to review, come in, because the Euler angles tell us how the airplane is oriented in relation to, there's that spot, to the Earth fixed axis system, because which way is gravity acting here? It's in the down Earth fixed axis system, right? So we've got to know, well, which way is down Earth in this axis system. So we'll spend some time on Euler angles. That's why I'm having you go back and review that from or spacecraft dynamics. On this axis system, we're still doing okay time-wise, yeah. This will probably be the last thing we do. Probably enough for the first day, maybe too much, but we got to get going. So in this body fixed axis system, we'll define linear velocities. U is forward, V is side, and W is down. So we'll talk about along the x of velocity U, forward, velocity V sideways, and then in the Z direction, a velocity W down. So with regard to our foam airplane, the speed forward is U. How fast the airplane is sliding sideways is V, and how fast it's falling is W. Although I shouldn't probably use the word falling because that implies gravity and all that. How fast it's going down through the air. So those are linear velocities, and then we have angular velocities. And that is P, Q, and R. This is pitch and so P is about the x-axis. And why did I choose that direction as positive? Remember how we define angular directions around an axis? You use the right hand, you point your thumb in the axis, and then your fingers tell you what positive is. So this is roll. Pitch is going to be like this. And yaw is R like that. The right-hand rule is the guaranteed way to get it right, but you can memorize positive roll is right wing down. Sounds kind of positive, right? Positive pitch is nose up. And positive yaw is nose right. So back on the foam airplane, positive roll is right wing down. Pitch, nose up. Yaw, nose right. I recommend that you put a paper clip on that page of the textbook so you can always find it. Because we will talk about, well, what is positive pitch? When we're talking about pitching moment, you'll need to go and remember which way that is. Oh, and what vectors? The total velocity here is just the three components put in a vector form, and we call that V. And then the angular velocities are the vector components of P, Q, and R. And so we call that omega, the total angular velocity vector. Like that. All right, the last thing that we need to do is define angle of attack and side slip, and I'm going to wait till next time to do that because it's important that we're fresh when we understand that. I know you've seen that before, but let's review it again next time. So remind me that that's where I stopped. Your assignment for homework, look on Blackboard. I will be putting the homework assignment there. And do the review. Your main assignment now is to do the review for the quiz on Friday. Oh, one last comment about the homework. The way I do homework in this class is the homework is assigned and it's given a due date on Blackboard. That's when you scan it and upload it. But the due date on the assignment sheet will be a day before, a classroom period before that it's actually due in class. I'm sorry, it's actually due on Blackboard. And the way that works is the class period before you upload it, I'd go through and give you some spot check answers for the homework. And you can ask me questions. And so the way this is intended to work, and I'll enforce this, is that you need to have the homework attempted by that day before it's due when you come into class. In other words, don't wait to watch what I do in class and then you go back and do the homework. I want you to try it on your own. Come in, because I'm not going to go through it all in detail. So you need to be able to sit here and I go, okay, the answer for the mean aerodynamic chord of the wing is 14.5, and you guys should be nodding your head, yes, that's what I got, or no, that's not what I got. Why did I get wrong? And then we'll figure it out. So work it ahead of time, come into class and be prepared to fix up. If you didn't understand what was going on or you got something wrong, you have an opportunity to fix it up before you upload it. Make sense? All right, so just a heads up on that. Questions from you guys or on the chat other than Yeah, there's some issues with the microphone. We're working on that. So thicker lines, yeah, I see that. Okay, I'll try. Just continue to remind me. I want to make sure you guys on Zoom can have as good of an experience as possible. All right, we're done for today. So if you guys on Zoom, I'm talking to the guys on Zoom now. If you're on Zoom, if you talk, does it not come through the system?
Well, can you hear me, Dr. Sack?
Unmute themselves. David,
Hey, Dr. Sack.
go ahead and talk. Yeah. No, I evidently do not have the ability to hear you.
Okay.
I'll ask Media Resources about that to see if there's something I need to reset to do that.
Awesome.
All right, see you guys.